Hello, we are going to discuss the electronic structure. That means what kind of electronic states materials have, why they have that kind of state, and what does it mean, how we can calculate the electronic states and the energy corresponding to that. All these things we are going to discuss now. So in order to discuss the electronic structure, we have to start from something very simple. And in order to start from something very simple, we have already discussed the case of hydrogen molecule, and now we will consider a one-dimensional linear chain of many hydrogen atoms. That's the next extension to the hydrogen molecule consideration that we have discussed in the context of covalent bonds. So let's consider a one-dimensional chain of n hydrogen atoms. We can draw the chain like this. So this is one hydrogen atom, this is second, third, fourth. Similarly, this is n minus 2, n minus 1, nth hydrogen atom if we have total n number of hydrogen atoms in the system. 1, 2, 3, 4, n minus 2, n minus 1, n, and here I draw the bonds between them. So this kind of a chain is something that we are going to consider now. Now each hydrogen atom is associated with an electronic S state. So we assume that these states, the atomic S states, they form a complete basis to represent the molecular single particle state of this system of hydrogen atoms, n number of hydrogen atoms arranged on a straight line. So if we consider the state of this entire system represented as psi, then we can expand psi in terms of the a linear combination of the basis elements as sum over j equals 1 to n coefficient Cj, which is in general complex, and the jth state. So j is this quantity, this ket vector j is the S state of jth atom. Now our task is to find the coefficients Cj. If we can find these coefficients, then we will be able to find out the state and the energy eigenvalue corresponding to the state psi. So we need to write the Schrödinger equation. Which is in its time independent form just an eigenvalue equation, H psi equals E psi, and this in terms of the linear combination of psi can be represented as j sum over j equals 1 to n Cj H Hamiltonian acting on the state J. So, this Hamiltonian is the Hamiltonian of this system chain of hydrogen atoms, and this ket vector J, this corresponds to the atomic orbital. So, not necessarily J is an eigenstate of the Hamiltonian. This quantity according to this eigenvalue equation becomes E sum over J equals 1 to n Cj J. This is the eigenvalue equation that we can write. Now, in the next step, we are going to multiply a bra vector from the left. Let's call it P. And if we multiply this, that means we are projecting these states on the state from the pth side, and this equation this eigenvalue equation can be represented by doing this as sum over J equals 1 to n Cj P H J equals, the right hand side is E times sum over J equals 1 to n Cj P J, inner product of P and J. So, this is the secular equation for the chain of n atoms. Now, this requires a few approximations and denoting the terms in certain way to be able to progress further. So, in order to be able to solve this, we assign the Hamiltonian terms, Hamiltonian matrix elements, that means these kind of terms, and the overlap terms, that is these inner products, in certain way. How do we do that? The simplest assumption would be orthonormality. That means we assume P and J, their inner product, to be the Kronecker delta Pj. That means when P equals J, this inner product goes to 1. When P and J are different states, then this inner product goes to 0, which is just the orthonormal condition, orthonormality condition. We have also assumed this orthonormality condition for the hydrogen molecule case. We can work out the problem without assuming this, but then the mathematics would be cumbersome for very little gain. That's the reason we are considering this to be orthonormal. So, this is about the overlap elements. How about the matrix elements of the Hamiltonian? For the matrix elements of the Hamiltonian, we consider the following. If we have the Hamiltonian matrix, the Hamiltonian operator sandwiched between two same states, then we call for all values of J this kind of matrix element as alpha, which is the on-site term. Not that for every system this must happen, but for linear chain of hydrogen atom it is going to happen, and this is something we consider for simplicity. And for all values of J, alpha is the same constant, that's what we assume. Then how about the matrix element being sandwiched between the Hamiltonian operator being sandwiched between two different states. If we have this kind of a situation, then we call it beta, which is a hopping term, rather hopping element, this is the on-site element. So the hopping element, if P and J are nearest neighbors, so we are going to restrict the hopping between two nearest neighbors, and if they are not nearest neighbors, P and J are not nearest neighbors, then this kind of hopping term is going to be 0. This is something we assume for simplicity. Okay. Now we can determine alpha and beta by evaluating the integrals or by fitting with experimental data, but for this particular problem there is no experimental data for a chain of n hydrogen atoms. So let's consider the theoretical aspects of it. As we have learned that linear combination of atomic orbitals, the method that we are practicing here, it is not very accurate, but we obtain a lot of physical insight into the problem by exercising this kind of a method. That's the reason we are going to do this. So we are not very much interested in the accuracy of alpha and the values of the alpha and beta parameters here, but we are interested in the fact that these parameters may be in principle determined and what kind of understanding we can develop from this kind of an approach. Okay. Now, if we consider different values of P, we can find different forms of this secular equation, this equation here, and if we write that down, it will look like, I go to a next page, for different values of P, we can, so that equation becomes, for P equals 1, it is alpha C1 plus beta C2 equals E C1. For P equals 2, we have beta C1 plus alpha C2 plus beta C3 equals E C2. Subsequently, for P equals 3, we can write beta C2 plus alpha C3 plus beta C4 equals E C3. Similarly, we can go up to jth term. There we can write beta Cj minus 1 plus alpha Cj plus beta Cj plus 1 equals E Cj. This is for P equals j. We can move forward just like that. For P equals n minus 1, we can write beta Cn minus 2 plus alpha Cn minus 1 plus beta Cn, this quantity equals E Cn minus 1, this is for p equals n minus 1, and for p equals n we will have for the end atom Cn beta Cn minus 1 plus alpha Cn equals E Cn. This is for p equals n. So these are the equations that we have, the series of secular equations for this system of linear chain of hydrogen atoms, n number of hydrogen atoms. So these are n number of coupled differential equations. And we need to solve them to obtain the values of the coefficients Cj, those values. Now if we substitute the quantity E minus alpha over beta with the parameter x, then the jth equation, this equation here, can be written as Cj minus 1 minus x Cj plus Cj plus 1. This quantity equals 0. This is what we obtain. And if we use a trial solution for Cj in this case, if we try Cj having the form e power I j theta, where I is the square root of minus 1 and theta is to be determined. If we try this kind of a solution to this differential equation here, the set of coupled differential equations, sorry, it's not differential equation, it's just coupled linear equations. There is no differential form in here. So if we put this kind of a trial solution to this coupled linear equation here, these coupled linear equation which is taking this kind of a form, then we can write the following: e power I j minus 1 theta minus x e power I j theta plus e power I j plus 1 theta, this quantity equals 0. Then x turns out to be, by simplifying this, e power I theta plus e power minus I theta, which makes it twice of cosine theta. So here our theta could be real or imaginary or complex. We did not determine that yet, and depending on that, what the kind of form of cos theta will also depend, whether it would be a genuine cosine function or hyperbolic function, that will be determined by that. So, if we here replace theta with minus theta, the result does not change, it remains the same, that we can see readily. Therefore, the general solution for Cj would be Cj equals A e power I j theta plus B e power minus I j theta, where A and B, these are arbitrary constants. How do we determine A and B? If we go to the end positions, that is the left side end of the chain, this first equation here, and right side end of the chain, that is the last equation here, these equations will actually help us determine A and B. So, if we consider P equals 1, that is the first atom of the chain, we can write C2 equals x times C1, and if we have that, then from this equation we can write from this equation here, we can, sorry, from the general solution is this, from this one we can write A e power twice I theta plus B e power minus twice I theta. This equals twice cos theta times A e power I theta plus B e power minus I theta. This equation is satisfied if we set A equals minus B. That means wherever we have B, we will put minus A, and if we do that, then Cj, this quantity becomes A e power I j theta minus e power minus I j theta. This is what we obtain. A is still an arbitrary constant and we did not determine its value so far. Now, let us do the following. Let us write down Cj as d sin theta. If we do that, what would be the value of d? D, as you can see, would be twice I A, which is another arbitrary constant d. And if we consider the other end atom, the extreme right atom, this equation here, then we can write down that C n minus 1 equals x C n. And once we have that, then in terms of d, the equation becomes d sin n minus 1 times theta equals x d sin n theta, which is twice d cos theta sin n theta. How did we obtain cos theta? Because x equals twice cos theta. By putting this in place of x, we obtained this quantity. And if we have this, then we can write that sine n minus 1 theta equals twice cosine of theta sine of n theta, which is sine n theta cosine theta minus cosine n theta sine theta. So, in this form we have the constant d cancelled out. We did not determine d, but we got rid of it as long as the calculation of eigenvalue is concerned. Okay, we can now rewrite this. So, d still remains arbitrary, yet to be determined. We can write that tan n theta plus tan theta this quantity equals 0. So, this sine n minus 1 theta has been represented this way, and now if we divide this quantity by cosine n theta, we will get this kind of a form, and we will see that it goes to 0. It becomes 0. Okay. With this kind of a situation, in other words, we can write sine n theta cosine of theta plus sine theta cosine of n theta over cos theta cos n theta. This quantity is nothing but this tangent form here is 0, which tells us that sine n plus 1 theta, that is the numerator, not the denominator, the numerator must be 0. And if that is true, then we can solve for theta as theta equals m pi over n plus 1, where m is an integer. We can see that theta is real. This is not imaginary, this is not complex, this is real. And we will have n distinct solutions possible for distinct values of m, while m can take the value of any integer, but by taking more than n number of values, it will repeat some of the solutions. That is obvious, it is a sine function, so some of the solutions would be repeated. It won't create new solutions. And now if we find out the allowed values of E, allowed energies, for this linear chain of hydrogen atoms with finite number of, that is n number of hydrogen atoms. So, the allowed energy values would be alpha plus twice beta cosine of m pi over n plus 1, where m can be taken in the range 1, 2 up to n. for distinct solutions. You can see that the energy eigenvalues here are discrete because m is an integer, n is a finite integer. So, the energy eigenvalues cannot be continuous for finite number of hydrogen atoms in the system. But if n tends to infinity, you can see that the energy eigenvalues will reach the continuum limit. Okay. Now, let us find the mth state of the system, mth eigenstate of the system, which we denote as psi m ket vector. And if we take the expansion coefficients Cj with this index m, where j can also have values from 1, 2 up to the number of atoms, then Cjm can be written as dm, d is not yet determined, sine of mj pi over n plus 1. So, in order to determine the state vector, we need to determine the coefficients of the basis elements, and in order to determine that, we want to find out this arbitrary constant d at this stage. So, how do we determine that? We can now use the normalization condition psi m inner product with itself this has to be 1 for orthonormality, and for that we need to have dm equals 2 over n plus 1 square root of this quantity. Then we have something interesting to find out, the eigenvalues. If we have n equals 1, we will just have one eigenvalue here, which is the atomic eigenvalue. If we have n equals 2, we will have a bonding state and an anti-bonding state. These are the levels, energy levels, as we have seen in the case of hydrogen molecule. If we have n equals 3, we will have 3 states here: bonding, anti-bonding and non-bonding, and so on. If we have n tending to infinity, then we will have a continuous spectrum of energy eigenvalues that you can see right away. Now, let us consider something interesting. We cannot really calculate for infinite number of atoms, but we can put periodic boundary condition in place. Which means 0th atom and n plus 1 atom, these are the same.